So this course has a website. You can access this by going to my homepage, Teaching and Concentration Inequalities. So all of the course related information will be updated here. Announcements will be made on Google Classroom. If you have registered for the course, then you will receive an invite by tomorrow or so. But whatever, by the second class, if you've not got an invite and you have already registered, then just let me know. Okay, so as I said, the prerequisites are probability and random processes. I'll assume that you've done some basic course. It's helpful to know some programming in Python. You won't use it extensively, but I'll perhaps just use it to give some examples and maybe an exercise or two. All right. And for assessment, there'll basically be 2 exams. I'll give homeworks along the way, and you can expect to see some of the homework problems appear in the exams. There'll be a midterm exam probably in the week of the 12th of August. And the final exam will be on 2nd September. It will be in class. The final exam will be in class. The first exam will figure it out. If you have any questions, you would like to meet me outside of class, you can send me an email and set up an appointment. My office is in Academic Block C, office 446. And classes will happen in slot P. We've already sort of adjusted it so that there are as few clashes as possible. So it may not be possible to change the slot anymore. All right. And references, list of topics, and class notes, all of these will be updated in this webpage. All right. Any questions with regards to logistics? Yes.
Is this course mandatory for EE?
It is not a core course for EE. I mean, anyway, for that you'd better refer your faculty, check with your faculty advisor, but this is not a mandatory course. But if you want to take a course on Introduction to Statistical Learning Theory or Kernel Methods, which are EE 5604 and EE 5605, then this will be a prerequisite. So if you plan to take any of those courses later, then you had better take this course. All right. Any other questions? I hope I'm audible at the back. If not, please come forward. Okay, so in that case, let's begin. So firstly, this will be an introductory class. So I'll speak a lot about what this course is about, where applications arise, and also we'll start with some basic prerequisites in probability. Hopefully you've seen all of this, but this will be a very quick refresher, just to essentially set the expectations. So what is this course about? As the name suggests, it's about concentration inequalities, which means that there's some form of concentration. A large part of something lies in a very small area, so to speak. Right? So this is essentially a probability course, and as it so happens, for certain kinds of phenomena, we observe that a large part of the probability happens to lie in very small sets. For example, suppose you toss a coin. All right. If you toss a coin once, what is the probability that you get a head? Half, right? So, what the probability of getting a tail is half, right? Assuming it's a fair coin. So really, you can't really determine whether it's going to be head or tail. But now I suppose I toss the coin 1,000 times. Right? What would you say is roughly the fraction of heads? Yeah, half. Right? So if you toss a coin a very large number of times, then you observe that the fraction of times you get a head is very, very close to half. Of course, the outcomes may be very, very different. possibly you get head, tail, head, tail, head, tail. You have a number of different outcomes. All of those outcomes occur with different probabilities. But no matter what happens, you know for sure that if you toss a coin a very large number of times, you will get heads roughly half of the time. So this is what I mean by this phenomena of concentration. Even though if you tossed it once, you could really not say whether it would be a head or a tail. If you had to guess beforehand, then you would be correct with probability half and wrong with probability half. But suppose you tossed the coin, let's say 10,000 times, and you had to predict beforehand what would be the fraction of heads, you would be very close to correct with high probability. So in order to see this, let's do a very simple experiment. All right. So let's say that let me just write a program to simulate this process of coin tosses. So right. So suppose I toss a coin n times. Okay. So let's start with n equal to 5. I toss a coin 5 times, and this is an experiment, right? So if I toss the coin 5 times, I get some particular outcome. This could be like head, tail, head, head, or something else. But let me repeat this experiment a huge number of times. Let's say 10,000 times. So I repeat this experiment 10,000 times because I want to know what is the probability that I get. I want to get an estimate of what is the probability of some event happening. And the event that I'm interested in is getting what is the fraction of hits. All right. So let me define okay, so I'll repeat the same experiment a huge number of times. So n trials number of times. So let me say that first I want to toss a coin n times. Right, so I toss a coin with a fair coin n times, and I just count the fraction of times I get a head. Right, I get either 0 or 1, 0 with probability half, 1 with probability half, and I just sum them all. And this is all that I do. Okay, just repeat this experiment so many times. And let's plot a histogram of what we get, right? The fraction of hits. Right? Any questions? So n is the number of coins that I toss. Okay. So every time I run this, I'm going to get one particular outcome. I repeat this a huge number of times. Exactly. So at every, well, for me, one outcome is 5 tosses of a coin. Yes. All right. I want to average this over a number of times. Okay. Is that clear? Any questions? Okay. So I ran this once. So this is for 5 tosses of a coin. What are the outcomes for fraction of heads? What possible values can this take? I tossed a coin 5 times and I counted the fraction of heads. What values can this take? 0, 1 by 5, 2 by 5, 3 by 5, 4 by 5, and 1. So 6 possible values. I did this 10,000 times and counted the number of times I got 0 by 5, number of times I got 1 by 5, 2 by 5, 3 by 5, 4 by 5. Apparently, I never got 5 by 5. Alright? This experiment makes sense. Alright? So I'm plotting this all the way from 0 to 1. So as it so happened, I got 0, that is all tails, around, let me see, around 300 times or so. I got 1 by 5. So the number of times I got exactly one head was roughly 1500, 1600 times, and so on. Alright? So now let's see what happens if I increase the number of coin tosses. So I had 5. Let me just make this 100. Now you see, initially when I tossed the coin only 5 times and I plotted the histogram all the way from 0 to 1, it was very nicely spread out, right? But now as I increase the fraction of heads, I increase the number of times I toss this coin, you see that, well, a number of possible outcomes are possible, but you see that sort of thinning down. So as it so happens, the number of times you get, the number of times you get fraction of heads equal to half is kind of high, but then you can see a whole different number of values, right? What happens if I increase this to 1000? The histogram becomes thinner and thinner. So this is what I mean by this phenomena of concentration. As you increase the number of coins you toss, or the number of times you toss the same coin, as you increase n, you see that the histogram becomes narrower and narrower, and a lot of which basically says that a large fraction of this probability is concentrated in some small set. In this case, a lot of the probability is around a half. Right? When I repeated this experiment a number of times, I almost never see fraction of heads being less than 0.4 or greater than 0.6. Right? And if I increase n, this phenomena is going to get even more extreme. right? It becomes more peaked. So this is something that you would kind of expect, right? But we'll make this more quantitative. We'll try to analyze what is the probability that the fraction of heads deviates from half by a certain amount. So this whole course will be in trying to derive bounds on such kind of concentration phenomena. So typically as you go, there's some parameter n, right? In this case, n is the number of coin tosses. We see that as this parameter n is increased, you have this kind of almost deterministic behavior, right? Even though the phenomena is random, you're tossing a coin n times, and you can't really say what the outcome is going to be, right? You can't really say with certainty what realization you will see, whether it's going to be head, 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 or head, tail, head, tail, head, tail. But as n becomes large, you can say that the fraction of heads is going to be close to a half. This is a deterministic phenomenon. So we'll see that as n becomes large, this behaves almost like a deterministic quantity. And that's what I mean by this phenomena of concentration. So more generally, what we are really interested in is the following. Suppose we have a sequence of random variables, then we want to know and we want to analyze some function of this sequence of random variables. We want to know how close this function is to its expected value. Effectively, all of this course is going to be in trying to derive bounds on the probability that some function deviates from its expectation by a certain amount. So essentially, we want to design bounds on the probability that some function right. So this is essentially the quantity. We want to derive bounds on this particular quantity. And we'll see a whole bunch of different ways to do this. So this seems like a very specialized thing to do, right? Where this whole course is about trying to derive bounds on this particular quantity. But why is this useful? Where does this arise? So one place that this arises, so essentially this arises whenever you have sort of large number of interacting particles or a large number of variables that we're interested in. So one classic example is in information theory and communications. So what is the problem of communications? We want to transmit some message. The goal of communication is to transmit some useful information across a noisy channel or across a noisy medium. And one very simple way of thinking about a communication system, a noisy communication system, is the following. You transmit something, let's say using an antenna, and you receive something else. What you receive is just what is transmitted plus some noise. Right? That's one of the simplest ways to model a noisy communication system. So y of I, so at any point in time, if you transmit something, you get the transmitted signal plus noise. Right? And the goal is to somehow be able to communicate despite having this noise. The goal is to be able to communicate such that whatever useful information you wanted to transmit across is somehow recovered reliably. All right, does that make sense? So the common way that we do in digital communication systems is the following. So suppose that you have some kind of a message, right? So the message could be a file that you want to transmit, or it could also be, let's say, voice signal, right? You're speaking to someone over the phone. Now this message somehow has to be encoded, right, converted to a form by maybe you add in some redundancy and so on and so forth. And then this is transmitted across a channel. So the original message, you can view this as a sequence of k bits. Maybe it's a file of, let's say, 10 kilobits. So you have a 10 kilobit file that you want to transmit across this noisy medium. And you don't transmit it directly, because if you transmit it directly, then some of the bits are going to get corrupted. You're never going to be able to recover what you transmitted exactly. So what you do in typical digital communication systems is that you add a certain amount of redundancy. So one simple way could be you sort of repeat the bits, right? Instead of sending the file, you send the file twice. But even this is not very good. So there are other ways, sort of techniques called error correcting codes, that you can use in order to sort of alleviate this effect of noise. So we're not going to worry about that, but it's just enough to understand that your message, which is your file, is going to be encoded into some sequence of length n, and this is transmitted across the channel. So you transmit n symbols one after the other through this particular channel. What you receive is xn plus some noise. And the goal of this decoder is to try to reconstruct what the message was from this noisy observation. Right? You can't get rid of the noise, that's there, that's part of the physical system. But hopefully this additional redundancy that you have introduced helps you to recover the original message from the received signal. Right? And any such decoder is essentially just some function of the received signal. So the most natural question to ask in such a digital communications problem is, what is the probability of error? That is, what is the probability that this reconstructed message, which is f of yn, is exactly equal to the message, or it's not equal to the message? And the goal of digital communication is to ensure that you can design this encoder and decoder such that this probability of error is small. But firstly, how do you analyze the probability of error? Because it's a really complicated quantity, n could be very large. And as we'll see, these concentration inequalities allow us to tell us something about yn, and in fact even get bounds on the probability of error for certain kinds of encoding schemes. Right? We'll see this application in a later class. Another application is in machine learning, something that we'll explore in a lot more detail in this particular course. So one sort of prototypical problem in machine learning is this problem of classification. Right? And the goal is to, let's say you have an image, you want to find out whether this image has a car in it or not. Right? So given any image, you want to know, you want to design some kind of a machine learning system, some kind of an algorithm which predicts whether this image has a car in it. And how do you do this? Well, you take a whole bunch of images and you feed it to some kind of a machine learning algorithm in order to design a classifier or a predictor. So what do? You have, let's say, a data set, which is, we just take a bunch of images which have cars in them, some images which don't have cars in them. And you know whether each image has a car or doesn't have a car. So this, you can think of xi as an image and this as the true label. So it's, let's say it's equal to 0 if there is no car and 1 if there is a car. All right. So you have this data set, which is also sometimes called the training set. And what do? Well, you don't really know the class of all possible images, right? All you have are a bunch of representative examples. Let's say you have 1000 images which have a car in them, 1000 images that don't have a car in them. Using just this, given a new image, you should be able to predict whether there is a car in it or not, right? Which seems like a pretty hard problem, right? So how do you design a classifier? Let's say maybe you want to train a neural network to do this. Okay. What is a neural network? A neural network is just a function. Given an image, it outputs either 0 or 1. It's just some class of functions which has a bunch of free parameters, which are the weights. We'll explore all of this in detail. If you've seen some of this before, well and good, you know what I mean. If not, don't worry too much about it. All right, so you can think of F as your neural network and alpha to be the weights of this particular neural network. The main problem in supervised learning or in classification is to choose the weights for which you best approximate this particular data set. You want to perform as well as possible over this particular training set. All right. So in other words, you minimize or you try to find out those weights which minimizes some particular cost. And what is the cost? Maybe it's the fraction of times you incorrectly guess that it's actually a car or not. That's one particular example. This is what is called a loss function. Again, if you've seen this, well and good. How many of you have taken a machine learning course before? Okay, that's a good fraction. So this is some particular loss function, and you run this optimization problem and try to find what is that alpha or what is the set of weights for which this loss is minimized. Remember, always keep in mind that this loss is minimized only over the training set. But what you want this particular machine learning algorithm to do or neural network to do is predict well over an unseen sample. If I pick a random image which is outside, which is potentially outside this particular data set, I should still be able to do reasonably well. Right? So the question is, how do you give such guarantees at all? Right? What is the basis with which you do this training and still expect to do well? All right, so that's the fundamental concept behind statistical learning. You make some assumptions. So for example, one assumption that we make is that this data set, it's not an arbitrary data set, but it's drawn randomly from the class of all possible images. Okay? So it is indeed a representative sample. Okay, so we'll assume that they're randomly drawn according to some distribution. We don't know what that distribution is, but still it's a good enough sample. And the assumption that we'll also make is that when we see a test sample, it's also drawn from the same distribution. So how do we quantify the performance of a machine learning algorithm over an unseen sample? One way of quantifying it is, for this specific example, we can ask what is the probability that f of xi, that is the output of the neural network, is not equal to the true label. That's a reasonable way of quantifying the learning algorithm. But one thing to note is that this, let me not call it xi, let me call it x. So this x is a completely independent sample. It's a completely independent image, potentially outside the training set. Okay, so want to know how good is this? How good is your learning algorithm? Another way of looking at this is, as we'll see, this can be written as expectation of some loss function and 1. So on average, how does this perform over a new sample? So this is what we are really interested in, but what we minimize at the time of training is this particular quantity. And as we'll see, as the number of test training samples is large enough, this turns out to be a very good approximation of this particular quantity. So even though you're training your algorithm over a really small set, it so happens that as the number of training samples becomes large, the performance of your training algorithm almost matches the performance that you get on your test data set or a completely new sample that you've never seen before. So we'll formalize all of these things as we go on. Another example that we'll see is in data compression. So what is the problem of data compression? Suppose you are given a large file, maybe which has n bits. The goal is to compress this to a much smaller file which still contains the same amount of information as the original file. So the end goal is to reconstruct the original raw file from this compressed file. Right. So the goal is to somehow be able to design a compression scheme or a compressor and a decompressor, sometimes called an encoder and a decoder, such that the size of the compressed file is as small as possible, but at the same time you can reconstruct the raw file. So this what you get from the decompressor is equal to the raw file, but maybe with some probability you are allowed to go wrong. So let's take a concrete example. Suppose that we know the statistics of this raw file. Right? The raw file has n bits, it's an n bit string, but the probability that xi is equal to 1 is, let us say, some p, where p is something that's less than a half. Right? So the fraction of ones that you see is something much smaller than half. Now if you didn't compress, how many bits would you need to represent this file? N bits, right? And hopefully you're able to compress it down to something much less than n bits. So the rate of compression is just k over n, and the probability of error is defined to be the probability that xn hat is not equal to xn. Okay, does this problem make sense? All right. So now, what kind of is this something that we've just seen previously? What does this look like? Yeah? Yes? I think someone said that. A biased coin toss, right? So you toss a coin n times. With probability p you get a head, with probability 1 minus p you get a tail. Right? That's, both of them have the same distribution. Correct? So what would you expect the file to look like? Okay, what can you say about biased coin tosses? As n becomes large, yes, what is the fraction of heads? Yeah, louder. I have a biased coin, probability of getting a head is p. I toss it n times, where n is very, very large. What is the fraction of heads? It's going to be close to p, right? Um, so using this, can you try to come up with a compression scheme that uses less than n bits? Intuitively, what would you come up with? Doesn't matter about its computational complexity or anything of that sort, but some way in order to ensure that you should still be able to recover the original file with high probability, but you can somehow store it using less than n bits. Can you speak up a little? Okay, suppose k is fixed. Okay, so k is fixed beforehand. All right, so you represent every compressed sequence using the same number of bits, but I don't necessarily represent all possible configurations of the input. That's okay. Okay, so which? Okay, how would you do that? So which event would have the highest probability? Sorry? Are you sure that's the event which has the highest probability? Which is the one that would have the highest probability? Or in other words, we have to be a little careful. Which outcome has the highest probability? Again, think about it a little. Which outcome, so which sequence of heads and tails would give you the highest, has the highest probability of occurrence? So the probability, so I'm assuming that the probability that xi is equal to 1 equal to p, and p is something which is strictly less than half, okay, for now. So it's a biased coin, and I toss this coin, or I observe n independent and identically distributed samples. Okay, what do you get? All heads. So in terms of zeros and ones, p is between 0 and half. It's the other one, right? All zeros has the highest probability of occurrence. So what is the probability that xn is the all zero sequence? What is the probability that this happens? Yeah. This is 1 minus p whole to the power n. What is the probability that xn is equal to some particular sequence of zeros and ones? What does this depend on? Yeah, so it is p to the power number of ones times 1 minus p to the power number of zeros. Correct? And when is this the largest? P is less than 1 minus p. So more the number of zeros, the higher the probability. right? So the all zeros sequence has the highest probability of occurrence, but somehow, even when we toss a coin n times, or in this case, the fraction of time, the fraction of heads that you see would be close to p, which is less than half. So is there a contradiction somewhere? Can you speak up a little? I didn't hear the whole. Mhm. Correct. So the main point is that each of these events, right, fraction of heads equal to half, fraction of heads equal to point whatever between 0.49 and 0.51, each of these are events, and each event consists of a number of outcomes, and the number of outcomes that correspond to fraction of heads close to half is more than the number of outcomes that correspond to, say, fraction of heads equal to 1. So how many outcomes give you fraction of heads exactly equal to 1? Yeah, one outcome, right? So, and what is the probability that you get this particular outcome as n tends to infinity? Yeah, 0, right? As n tends to infinity, this tends to 0. Right? So, in general, what is the probability that the fraction of ones is equal to, say, k by n, or let me call this m by n? Yes. Yeah. So it's equal to n choose m. I'll use this to denote n choose m. Okay. Speed over n minus m. Right. So since the fraction of ones is equal to m by n, the number of ones is equal to m. Right. So that's why I have a p raised to m. Number of zeros is n minus m, so it's equal to 1 minus p whole raised to n minus m. And how many sequences of length n have exactly m ones in them? That's n choose n, right? Great. So then I'll leave this as an exercise. For what value of m is this quantity maximized? Sorry? I leave it as an exercise. That's not true. Okay. Now this in itself is hard to manipulate, all right, because you have an n choose m. So you can look up the following on, let's say, Wikipedia. It's called Stirling's approximation. It's a very good approximation for the binomial coefficient, for particularly for large n. Okay. So I'd say you apply Stirling's approximation on this n choose m and try to use your favorite technique to maximize this particular quantity. Right? But really, if you think about it intuitively, which m do you think, or for what value of m by n do you think this should be the largest based on experience? Yeah, p, right? Because you know by experience that if you toss a biased coin, the fraction of times you get heads should be close to p, right? So really the math should work out only if this is maximized when m is equal to n times p, right? And in fact you can try that out. It's a good exercise. Okay, so again, how does this help with a problem of compression? So one way of designing a fixed length compressor is the following. I know that the fraction of 1 should be close to p. So what do? I just list out all possible sequences which have roughly p ones. So let's say the number of ones is greater than or equal to some p minus delta, but it's less than p plus delta. I just give some small amount of slack. All right. It's a very inefficient approach, but let's say I list all possible sequences for which this happens. All right. And so I list all of these sequences and just label them. Let's say this gives me the size of, so C is this particular list. How many bits do I need to represent all sequences in this set C? This is some subset of binary sequences, right? This C. Suppose I had to assign a unique label to each of these sequences. How many bits would I need? Yeah? Log of the number of sequences, right? So I could choose K to be equal to log of the number of sequences, maybe with a C. Right? These many bits are enough to uniquely represent every element of this particular set. Right? So now if C is small, then K is small, and I've got some compression. And again, with my hand waving, I'll say that C has very high probability. The probability that the fraction of ones is away from P is very, very small. Right? So the probability of error is the probability that the number of ones in Xn is greater than or equal to P minus delta, greater than or equal to P plus delta, or less than or equal to P minus delta. Right? Which is, I'm just saying that it's going to be small. So the main point that I'm trying to make is that you have a bunch of these different problems, And in each case, I can somehow reduce the analysis of that particular problem down to bounding some probability which involves a very large number of random variables. And this concept of concentration essentially says that if you have a large number of random variables, then certain functions of these behave like they're almost deterministic. That only certain events can happen with high probability, all other events occur with very, very small probability. All right, does that make sense? Okay, so now let's take a detour and quickly recap some concepts in probability. All right, so I need your help from this point on. What is a probability space? Have you seen this before? Omega, F, and P. Okay, what is omega? Called the sample space. And represents all possible outcomes that you can possibly observe. Right? Can you give me some examples of sample spaces? Yeah. Can you speak up? Okay, so for example, if you're tossing a coin, then your outcome could be head and tail. Right? That's one sample space. If I'm tossing a coin, say twice, what would be the sample space? Yep, so all possible combinations, head, 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 tail, tail, head, and tail, tail. Right? If I am, let's say, generating a random number between 0 and 1, what would be the sample space? So the interval from 0 to 1. Right? All of these are examples of sample spaces. Okay, what is F? Yeah? Set of events. So let's call this the event space. And it is a collection of subsets of omega. Right? Is it allowed to be any collection of subsets? Okay, what properties does it have to satisfy? Okay, so something even more basic. That's true. So it's some collection of subsets of omega by definition, but union of all events. So firstly, is it necessary that it's non-empty in the first place? So omega should belong to F. Right? In fact, we'll see that the empty set should also belong to F. The next, okay, so if some subset A belongs to F, then the complement should also belong to F. Okay. So if I have a countable collection of sets all which belong to F, then their union should also belong to F. So just let's just take rolling a single die. All right, so omega is the set of all possible outcomes are 1, 2, 3, 4, 5, and 6. What would be the smallest event space that contains this particular set? Yeah. Okay, one itself has to have omega and the empty set. Three, 4, 5, 6. Anything else? That's it, right? So what would be the smallest event space that contains the singletons 1 and 2? So omega and the empty set should be in the event space. Obviously 1 and 2 should also be in the event space. What else? The union 1, 2. What else? Essentially the complement of 1, which is 2 up to 6. The complement of 2, which is 1, 3 up to 6. Three up to 6. Anything else? Any other sets? Okay, so here's a question. Why do you need the event space? I'm sorry? Okay. Why not? Okay. Why can't I assign probabilities to outcomes? Is the question clear? So why do you need this concept of an event space? I've defined all possible outcomes, right? The sample space contains all possible outcomes that you see, right? So why do I even need to define this event space and sigma algebra and why does the sigma algebra have to satisfy these properties? Sorry, can you repeat? Can you repeat? Okay, but why can't I just do that with the sample space itself?
Space contains all time.
Okay, but if I know, can't I always define a probability measure on the sample space itself? So how do you define the probability measure formally? So, so what is a probability measure? So the probability measure assigns for every event some number, right? And what properties does this have to satisfy? What else? Right, so this is how you hopefully have seen the definition of a probability measure in your random variables course. So first question you should ask is, why are you defining it over f and not over omega? Well, if you define it over the sample space, then no matter what event you define, you can always get it, right? I don't know, you just tell me the probabilities of the outcome. If I tell you how exactly I get each outcome, is that not sufficient? Why do you need this formalism of an event space, and why can't you just work directly with the sample space? Is that a question you have? There's no notion of independence here, right? There's only one experiment.
When we talk in terms of best sample space,
Okay.
and we are sending the probability outcomes as such, we are not able to create certain.
Again, we've not come to independence at all, right? I'm talking about something much more basic. So let's take the example of, let's say, tossing n coins. Okay. How would you describe the random experiment? How would you assign probabilities? You assign probabilities to outcomes, right? You say that the probability of getting head-head is 1/4, head-tail is 1/4, tail-head is 1/4, and tail-tail is 1/4. Right? Or if it's a biased coin, then head-head is p square, head tail or tail head is p into 1 minus p, and tail tail is 1 minus p the whole square. Correct? Well, if I can, why can't I do this for in all cases? Here I have defined the probability measure on events, and events can be arbitrary subsets. If I know the probability of each outcome, then I can get the probability of any arbitrary event. Correct? So where does this break down? The probability of individual outcome infinity. Okay, difficult. Why? Okay. 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 So let me just repeat what he said. Now, everything is fine when your sample space is finite, right? Or even if it's countably infinite. But as soon as the sample space becomes uncountably infinite, you no longer be able to assign a measure or assign probabilities to each individual outcome. So suppose you toss a coin infinitely many times. That's a random experiment. Okay, you're tossing it infinitely many times, but I can still consider events that make sense. For example, I'm tossing it infinitely many times, but I can still talk about events where the first 10 tosses give me heads. That's a valid event, right? But if I'm tossing it infinitely many times, what is the probability of each outcome occurring? Yeah, it's 0, right? The probability that a particular outcome, that you see a particular infinite sequence, that is equal to 0. So you can't obviously assign probabilities to individual outcomes, right? So when omega is uncountably infinite, you cannot assign probabilities to individual outcomes. You can only assign probabilities to events that make sense, right? So you assign probabilities to certain basic events and then hope that everything remains consistent. So in the case of tossing infinitely many coins, how do you assign probabilities? How do you define a probability measure over infinitely many coin tosses? Yes? Okay, but what is the event again? There are of course different ways of defining a probability measure over this experiment. One way of doing it is you say that the probability that for any I, xi equal to head is equal to p, and the probability that xi equal to tail is 1 minus p. So this tells you what is the probability that each individual toss is head or tail, and then you can do this for pairs of coin tosses, triples, and so on. So for any xi xj, and so on. Right? Note that each of these corresponds to an event of the original sample space. The original sample space consists of infinitely many coin tosses. So in this case, you're zooming into the ith toss, right? So there are infinitely many outcomes that correspond to this particular xi equal to head or xi equal to tail. And similarly, xi equal to head, xj equal to tail, and so on. Right? So if you're able to say the probabilities of finite subsets of these coin tosses, then as it turns out, that's enough to specify the entire probability space. Right? So this is the way that you're used to defining a probability measure on infinite sequences. Right? So again, you should note that this is an event, right? Each event, this event corresponds to infinitely many outcomes, right? There are infinitely many outcomes that contribute to this particular event. Because let's say x1 equal to head would mean head followed by all possible combinations. So each of these, so you define the probabilities of each of these events and hope that this remains consistent. That there is that is why you need to be careful. That brings me to the other question. Why not choose the event space to be all possible subsets of omega? Can you always choose the event space to be all possible subsets of the sample space? I hope you know what is meant by a power set. A power set is just set of all possible subsets of the base set. So can you always choose F to be the power set? How many say yes? How many say no? Okay, you have to raise your hand up high. How many say no? You cannot choose F to be the power set. Up high. Okay, how many say yes, you can choose F to be the power set? Okay, what about the rest? Okay, if you say that you can't choose F to be the power set, why can't you choose it to be the power set? Okay, can you speak up a little? Yes. Null set, so that null set always have probability 0, right? So it's the event that nothing happened. But that's not a contradiction, right? Correct. So doesn't matter. So remember that the sigma algebra always has to have phi, right? Because if you combine these two, then it means that phi is in F, right? So then what is the problem with choosing F to be the power set? That's okay. Yes. So, so what? You're close. Okay. Doesn't matter. Why won't you be able to assign if the power set is uncountable? The problem is, as it turns out, consistency. So, as I said, you need to be able, so how do you define the probability measure? You first try to define it over some base subset, some basic sets. For example, let's say you try to assign probabilities for all intervals. Suppose my omega is the set of all real numbers. Okay. What I can do is, let's say I assign probabilities to all possible intervals. Okay. So I assign probabilities to intervals of the form a comma b. So for every interval a and every interval a comma b, I somehow assign a probability measure which is consistent, which doesn't violate any of these properties. Okay. So even if you don't think about probability, let's say you want to just assign a measure. Okay, what is the most basic measure on an interval? Yeah, the length of the interval. So let's say mu of any interval a comma b is just b minus a. All right, this is how I'm defining a measure. The question is, if I assign this, so now I know this measure for all possible intervals. If I take union of two intervals which are disjoint, it's just going to be the sum of the lengths, which is our natural concept of a measure, or the length, right? But as it turns out, if you choose all possible subsets, this measure will not be consistent. There are certain sets for which, if you define this as the measure, then you can try to compute the measure on that set in two different ways and you'll get two different answers. So in order to avoid this inconsistency, you try to only look at sets which can be essentially generated by a countable union or intersection of intervals. Right? That's why you look at a very strict subset of the power set. So if you're interested, you can look at this particular topic or this particular set called the Vitali set. This is one example of a set where if you define this as the length or the length of a particular set, then the Vitali set cannot be assigned a unique measure. You can try to compute the measure in two different ways and you'll get two different answers. So let's stop here. We'll continue in the next class. Any quick questions? Okay.